Hello, folks, and welcome to Rational Science. Um, we have a great show today, busy show, and so we're going to get right to it. For those of you who are new, um, we divide our lecture in three parts. First part, we deal with extinction, quite a popular subject, really. My favorite is Neanderthals. I do quite a bit of research on the Neanderthal, love the subject, and so I dedicate some time to that, aside from physics. Then we're going to do a little bit of physics. Today's tunneling day. We're going to figure out what tunneling means or is for the purposes of quantum mechanics. Maybe like wormholes in general relativity. I don't know. We'll find out. And then at the end, we're going to open the floor for comments that have been made since the last time that I had my lecture. So, if you have questions, put them down. We try to address all the questions, and what we do, we address them at the next uh, lecture. And the main reason for that is that you want to have a good answer. And sometimes, those answers right off the cuff are not the best of answers. So it's good to figure out what the person's asking and so that you can answer the question properly. Okay, so let's get started. We're going to do a little bit of extinction and or subjects related to extinction. Remember here we're saying that the global economy is going to collapse. And by the way, I have a tremendous toothache. Um, I wasn't going to give the lecture today, but I put an aspirin against my gum, and apparently that calmed it down. So I hope I can do it all right. If I don't smile too much, you know why. See, when you get to my age, I'm going on 69 this year. Well, you can't fight gravity forever. Sometimes gravity wins, and your teeth start falling down to the ground. Okay, so here we go. First issue has to do with a comment I made the other day, really, which was related to Google, Apple, and Facebook. Some of these companies are being regulated. Regulated, they want to break them up maybe because they're too big, like they did with the baby bells. That's one option. Another option is to tax them at a higher rate, especially in these days of COVID, where they've taken such draconian measures, the politicians, to keep people inside the houses. A lot of people are out of work, and so they got to get their taxes from somewhere, and I guess they're going to tax the big corporations. And there was a lawsuit or an action by the European government, French government specifically in this case, against one of these big corporations. And here you see it. France fines Google 500 million euros in new copyright row. Actually, it was closer to 600 million euros, which is like 700 million dollars. Okay, so a big fine against Google. I'm not sure if they're going to appeal it. I'm not sure if they can. And it says long-running battle has centered on claims that Google has been showing articles, pictures, and videos produced by media outlets when displaying search results without adequate compensation, despite the seismic shift of global advertising revenues towards the search giant. Okay, so that's the main gripe against Google. And faced with dwindling print subscriptions, media outlets argue that Google should be giving them a bigger cut of advertising revenues from search results that display their content. Okay, and Google's argument was that some of these companies they get their revenue by traffic being diverted to them, and these companies say that's not enough. You should also give us a piece of the advertising revenue. That's what this case was about. And friends, competition watchdog. Competition watchdog? What the hell is that? On Tuesday, slapped Google with 500 million euros, 593 million. Oh, dollars. Okay, maybe I was wrong. $600 million. Fine for failing to negotiate in good faith with media companies over the use of their content under EU copyrights rules. The biggest ever fine imposed by what? The Competition Authority. See, it used to be the antitrust, now they call it the competition authority. Anyways, they're going after some of these big companies, and the question is whether, first, whether it's a good idea. That's one question, because you would think that, assuming that if Google becomes richer, it becomes bigger, it hires more people, and you would think it puts people to work. That's one way of looking at it. Another way of looking at it is that maybe they're already too big. Maybe you got to break them up, okay? Like the baby bells. Another one is that maybe you should tax them at a higher rate because they're making, uh, you know, um, terrible uh, profits, okay? Maybe we should spread the good the bonanza around, among the people somehow through government. So there's all different philosophies and political ways of addressing the issue, and the question is, which one will they follow? Okay, but apparently they not only them, but I was reading that Australia and some other countries are also trying to target these big corporations, and they're either going after their taxes or regulating them, or maybe even suggesting that they should be broken up. Again, we don't know what's going to happen there. Okay, more closer to extinction, we had some questions on the Neanderthals. Okay, again, a subject I absolutely love. Okay, and this fella says, out of Africa hypothesis is really fragile. An idiot, in my opinion. And new evidence Neanderthal skeleton was recently found in the Middle East, and it is older than European ones. Okay, Middle East, I guess it could be Israel, maybe Syria, maybe Iraq. They found some caves there, and they found, allegedly, Neanderthal skulls or bones or fossils, okay? And based on those finds, they reach conclusions, okay? This fellow read something, I don't know where, he didn't give any reference, but he says that Neanderthals that were found somewhere in the Middle East are older than European ones. I don't know, I have great doubts. Okay, here's the oldest one we have, the oldest skull we have of a Neanderthal, and that's the, can you get it up here? Go on the other side. Give me a second here. And this is the oldest skull is from Italy, Sacco Pastore, number one, and that's 130 to 100,000 years ago. And again, wide ranges because the farther back in time, the harder it is to date. Usually they date it with things that are around there. You can't carbon date these because carbon dating doesn't go beyond 50,000 years. So you look at other clues and you reach an approximate date. That's why the range is so wide. Okay, that's Sacco Pastore. That's supposedly the oldest Neanderthal skull we have today. Okay, and that's in Italy. And I don't think you'll find one in the Middle East. And here's an even older one, and this is not a Neanderthal. It's his forefather. This is Heidelbergensis, the Swanscombe skull, approximately 400,000 years ago. Again, very wide ranges here. Okay, maybe 400,000 years ago, and that came out of England. And it's not really a man. It's a woman, first of all, a female, and it's not a Neanderthal. It's their parents, Heidelbergensis, Homo heidelbergensis, and so what this shows. Okay, together with some other evidence that's out there, is that there were two-legged creatures like monkeys, like gorillas, like humans, something like that, in England. Okay, and so if they were there already at that time, and the theory is that Neanderthals descended from them, then Neanderthals were born in Europe. By the time maybe Homo erectus, maybe Heidelberg, one of those, was out. Then came Neanderthal, which descended from that group that originally was in Western Europe. So, if you follow that line, then you cannot think that what this individual is suggesting, which is that maybe, perhaps, the Neanderthals came from the Middle East. Okay, so I don't know about what this fellow is saying there. I don't accept that hypothesis. I don't use that as an assumption. I say that the ones that the skeletons, the fossils, the bones that we find in the Middle East are not at all Neanderthal. There's some other species. Okay, and I'm just gonna one more time show you this. Okay, and this is a paper written by experts who look at these bones, and they give you their 5 cents worth, again, their opinion. But, they say that the bones that they find in Israel, especially, and also the ones in Iraq, they found a cave there as well, full of bones. And they say that there is actually little evidence for the existence of a Southwest Asiatic Neanderthal population in Israel during the Middle Paleolithic period. Human fossils originally labeled as Neanderthals were subsequently reevaluated and defined otherwise. A horizontal mandibular foramen, they go out there and they say, which characterizes 61% of the Neanderthals is absent, and they mention 3 of the sites there, Shandar being one in Iraq. Okay, so the Neanderthals, the alleged Neanderthals that you find in the Middle East and the Levant, they don't match exactly. There are significant differences, in other words, with a Neanderthal, the original, the classical Neanderthals of Western Europe, of Spain, France, Belgium, and Germany, and possibly England if they ever find one there. Okay, they haven't found really a bone there, but don't put it past them. Someday they might. Okay. Anyways, these folks seem to say that what you see in the Levant are not Neanderthals. And the reason I like that proposal, that assumption, that theory, if you want, is that I cannot imagine Neanderthal, who I make the assumption that they were born in Europe, from first from going farther back, right, from Homo erectus, and then from Heidelbergensis, man of Heidelberg. I think that's the line that gave origin to Neanderthals. Once the Neanderthals were born, they were born in the cold, they were born in the Arctic, they were used to that weather, they were polar bears, they were like the woolly mammoths of human woolies, woolly man. And so, not only they did not need clothes, but this was their natural habitat. And so they had no problem. They walked in the snow. They could even sleep in the snow. They were built for the snow. And such an animal, such a creature, I don't think would go to the Middle East, farther south, where the warm weather was raging, closer to the equator. It's like you're asking a polar bear to go to the equator. Does that happen? I don't think so. Okay? And I don't think Neanderthal had any reason to go farther south because he had a lot of game. And as far as I'm concerned, humans came out of Africa. They went through the Middle East and they went north. And the reason is why? Well, I think they were either following the herds or they were looking for food and they found more food up north than in the south, and they ventured into Europe. And when the Neanderthals were gone, they settled in Europe, and they lasted, to today. And the reason for that is there was enough game in the north. There was not enough game in the south. Apparently, that's why the migration was northward. There was no reason, for climatic reasons and for food reasons, for the Neanderthals to go south to the Levant. And so, this is my little map on that. Okay, I'm saying that there's no chance that the Neanderthals, which were probably like gorillas, somewhat like them, in other words, they were the woolly man. I don't think they would go south to mount camels in the Middle East. No, I think they stayed up north where they hunted woolly mammoths and uh, the European buffalo and so on. There was no need for them to go south at all. And so, those investigative researchers that claim that they found Neanderthal bones in the Middle East, well, uh, they should think again. I don't think Neanderthals ever went south. I think they stayed in Europe and above a certain parallel, certainly around Italy and upwards. Okay, that's I think their range. Another fellow says regarding clothes. Remember, I'm saying that Neanderthals did not wear clothes at all, any footwear or anything. And this fellow said instead of searching for because I'm saying that the needle is one of the arguments against clothes. We haven't found any needles in Neanderthal sites, and we have over 80 sites in Europe where they found Neanderthal either bones or tools or some evidence of presence of the Neanderthals there, and they never found a needle in any of these sites. And you would think that one needle, made of bone, we would have found something like that. They found other things that are made of bone and wood that survived, and we never found a needle out of 80 sites. You would think that if they all wore clothes, they all had needles. The women, maybe, I don't know, it was a division of labor and she did, the women did the sewing. I don't think there's no reason for us not to find at least one needle, okay, in all these sites. And so, they found bones, tools, and weapons, but in about 80 Neanderthal sites, but no needle. And needles appear in the record approximately 36,000 years ago. In other words, we're talking about Cro-Magnon. And here I give you a little evidence, okay? This is the first needle we have on record, the Kostenki needle in Russia. And it's dated anywhere between 20 and 36,000 years ago. Okay, and yeah, that first one there does look like a needle. Okay, letter A there. So I would think that is a needle, and that's maybe when they appeared. And I think it may have appeared, again, 36, 30, maybe I'll take it even up to 40,000 years ago. As soon as humans, Cro-Magnons, entered Europe, it was cold, and they probably started building clothes. That's when clothes, I believe, were invented for the first time. Yeah, that's what it appears to me. There's another argument that it has to do with lice, and you can look that up. That's another argument out there, and that dates close to 175,000 years ago at least. And I disagree with that because I don't think man in Africa needed clothes. Okay, but they say the argument is that lice went from body lice to hair lice, and that's because they started wearing clothes. Okay, so that's the argument in a nutshell. Okay, anyways, they found a wooden spear 400,000 years ago. That's this little thing here, the Schöningen spear in Germany, and so it's made out of wood, and yeah, wood does tend to survive sometimes, under certain conditions. If this survived, why didn't the needle survive 40,000 years ago? Okay, so we're talking about 10 times as far back, and it's there, and we don't find a needle 40,000 years ago. So again, my argument with all this is that you have to look at the entire evidence to find out what evidence might fit the facts. Okay, of course we are selective with evidence many times because we want to get our theories through, and one piece of evidence maybe negates our theory, and so we kind of sweep it under the rug, so to speak. You got to be honest with yourself and look at all the evidence. And I try to look at pros and cons of all the arguments as much as possible, as much as I can find. I reach my own conclusions, and all I can do is just share my 10 cents worth with you. My idea is that Neanderthals were born in Europe. They had no reason to go south. They wore no clothes. And humans never entered Europe until the Neanderthals were gone, because otherwise the Neanderthals, who were in their own turf, which did not need clothes, they knew their environment. They probably marked their territories, I don't know, by spraying urine all over the trees, to ward any enemies, even on another Neanderthal, because Neanderthals were the worst enemies of Neanderthals. Okay, the only guy who could bring them down was another Neanderthal, just like a lion is the worst enemy of a lion. So I think the Neanderthals were born in Europe. They never left Europe. They had no reason to. There was enough game there to keep them busy and fed. And only when their population pyramid overturned, that's when they were gone, and humans were finally able to enter into Europe and find all these bones, these skeletons, whatever they found there, and they said, okay, someone was here, but he's gone. They probably thought it was another human. Okay, that's the way I see that in general terms. Okay, continue with cold. Neanderthals cold. People are wondering about that, right? Fellow says you could use the toothpick to poke a bunch of holes in hides and then just weave the string through the holes without even using a tool. Yeah, correctly. But the issue is that needle, is what we haven't found. Okay, so there's no evidence, at least, of it. I wish there were, to show that Neanderthals wore clothes. I don't think we're going to ever find evidence of needles. Okay, because I don't think they ever invented the needle. I don't think they ever did sewing. And you need to sew hides together in order to prepare clothes. You can't just, throw something on top of yourself. And I don't think they would have done that anyways. They weren't into that. I think they didn't need clothes. Okay, so there was no need for them to invent something they didn't need, any more than a polar bear needs something to cover itself. Okay, then you would have hide clothing. You would have hide clothing instead of freezing to death. Yeah, again, see, these people think that a Neanderthal would freeze to death. He was there 400,000 years or so, maybe less, maybe more, and he never froze to death. Why would he freeze to death? Okay, if he was made for the cold. Does a polar bear freeze to death? Does he know what cold means? Okay, even a dog is smart enough to get under a blanket. Yeah, maybe your puppy, at home, the domesticated dog, the one that's already been living thousands of years with man inside a house. He's not used to the cold. You can't take your dog to the I don't know, to the polar regions, to northern Canada or northern Russia, and just let him go there in the freezing snow. He's gonna die of frost. He's gonna die of cold. But that I know of, no polar bear dies of cold. No wolf, none of those die, okay, of cold. Another major motivation for inventing clothing is shoes. If you don't wear some kind of footwear outside, you'll die a lot faster. Yeah, you will. The question is whether a Neanderthal would. Or at very least, you'll be experiencing tons of pain, like walking on hot shards of glass or Legos. Nobody can tolerate that shit for long, even if they had Neanderthal feet, especially not females. Poor Neanderthal females, they had to go in the high heel shoes so their feet would touch the snow, I guess, right? Okay, let me wisen this guy up, this poor fellow here. He's so mistaken. Wolves don't usually wear clothes, but apparently some of them, wear these nightcaps so they don't freeze their ears. Polar bears, they put on gloves, even if it's baseball mitts, they don't care as long as they have their hands warm. The mastodons, they put on their their diapers there so they have their butts warm. And the woolly rhinos, they wear socks. They have to do that because otherwise their feet will get cold. And then you see the penguin and the penguin's feet. Now, the feet are directly in contact with the snow. I mean, do they wear shoes? So the question is, do these animals need clothes? And this fellow seems to think that they do, and maybe he should go out to the North Pole somewhere, or wherever these animals are found, maybe the South Pole, and put something around them so they won't freeze to death. Okay, so no, I think this fellow is so mistaken, and so many people believe like he does that. These animals would freeze to death. And they don't understand that they don't. These animals are built for cold. And here's the good old Neanderthal. You know, he's got to wear his earmuffs and sandals, for otherwise he's going to get his feet cold. That's what this fellow believes. Okay? So yeah, I doubt that very much. I don't think Neanderthals had anything to do with the cold. They didn't know what cold was. They never had it in their dictionary. They never say, "Oh, it's cold today." Never happened. Okay? They were born in the snow. Okay? They lived in caves. You know, they probably had fires as well. But when they went out, they didn't dress up and say, "Oh, it's cold outside. I think I'm going to dress up." No, no, they just went out like no problem. It wasn't an issue with them. They could go out in the cold, and if they used fire, maybe they used it for cooking. You know, we don't really know exactly what they did with the fire. I would think they did some cooking. Okay, but other than that, Neanderthals did not need, and they did it also for defense. You know, they realized that with fire they could keep some, some animal like a bear out of the cave. So they understood that they used it as a weapon. Other than that, you know, they could go out there and be in the snow every day, no problem. And you might say, well, is that true? Well, here we have a case in modern day history. Okay, now this is the 19th century, but it's still, you know, 100 years ago. Okay, and it was found by Mr. Darwin and Robert Fitzroy. Okay, and they were the Yagans. Okay, they were also known as the Fueginos because they're from Tierra del Fuego, south of Argentina and Chile. Okay, and that's in 1883. They were essentially nude, and this is 50 years after Darwin saw them. He saw them in 1833, and he put it in his diary. So did Fitzroy. And what they said is that the women, especially, you know, they would dive in the water after their husbands harpooned some fish or some animal from the seas, and they would pull this thing out. The women did the diving, and they also dived for seashells, collected seashells, and they were nude in the South. And the British were completely astonished by the resistance that these Yagans had to the cold. And there you see 1922, they were civilized by them somewhat, and they started wearing clothes. But before then, they were nude. And so look up where Tierra del Fuego is, south of Argentina and Chile, and you tell me if you could live there, nude. Okay, if you want to do start your nudist beach over there, you'd starve to death. Nobody would take off their clothes down there. And the young'uns had no problem. They lived like that down there. Okay? So if humans can do it, and I'm sure the Yagans were not as well protected as the Neanderthals, forget it. The Neanderthals had no problem whatsoever with the cold. They had no idea what cold was. They never had the word in their dictionary. Okay, talking about cold, we have someone talking about the Cold War. I know a little bit about that. And it says, looks like the USA lost the Cold War long term. Ha ha ha. Okay, remember the Cold War was originally only between the USSR, the Soviet Union, as it became known later, the UFSSR, which means the Union of Fewer and Fewer Socialist Republics. UFFSR. And today, well, yeah, they've stretched their hands across the divide there with China because they both have a common enemy, and the United States is blocking a lot of their stuff. So they decided to form a little bit of a partnership there against the United States. But the way I look at it today, you know, I look at it very differently when I was in my 20s. There, I used to think of the United States as an enemy. That's how I was raised. That's what I saw around me. But over time, you know, you start seeing things a little more clearly. And the way I look at all these is as mafias. They're all mafias. Okay, it doesn't matter if it's the United States, any country in Europe, Russia, China. They're all mafias. They all have politicians who rule, and they try to do whatever they can to get their countries rolling, or maybe just to become rich themselves and their friends. And the way I look at it, I don't pay attention to politics anymore. And the reason for that is, if you can't do anything about it, why even get excited about it? So Israel is torturing the Palestinians. You have war between Pakistanis and Indians. You have fighting, just about everywhere, really. China against Taiwan and so on. There's hot spots all over the world. Any one of them can break, the peace out there. Am I concerned anymore about all that? Not at all, because again, I can't do anything about it. So why get excited and say, well, this is justice and that's injustice, and if I can't do anything about it? So the best way I always recommend to any of you out there, the best way to deal with the world problems, to solve them, is turn your TV off. You turn it off, you solve the problem for yourself. Okay, that's the way you should look at it. Okay. So yeah, I don't worry about the Cold War anymore. My only concern there is I hope all these countries, the United States, China, and Russia, I hope they keep going upwards, and so that we live at least another 50 years, if we could do that. So I don't care if they torture, if they kill, if they murder. I really don't care, as long as it's not me, no problem. My only hope, if that's what they need to do to get the economy rolling forward, do it. I don't care. I'm not going to even look. I'm not going to question it. Okay? I don't care, because my only interest is that the world continue as much as it can. Because again, I'm saying, the last generation of humans on Earth. So I don't care how they do it. I don't care if it's illicit. I don't care if it's immoral, if it's unethical. What the governments are doing, I don't care. I really don't. It's not my problem anymore. It used to be my problem. I used to lose sleep over it. No more. I just turned the TV off. Okay, another fellow along the same line, more or less, says a system of fiat will always collapse. Power can corrupt. Absolute power corrupts absolutely. Famous saying. Okay. The only thing I got to say about that is that corruption is not what's going to cause the extinction of man. I just want to clarify that, okay? What's going to cause the extinction of man is this: the overturning of the. This is not what's going to cause the extinction of man. The overturning of the population pyramid. We are overturning. That's going to trigger the collapse of the economy, and that's what's going to cause the extinction of man. In other words, the overturning of the ecological pyramid. We're going to have the many, 8 billion humans, chasing the few, food. There's going to be no food out there. Why? Because we're not going to produce it, because the global economy, money is going to be no more. And because money is no more, no one has any incentive to produce it massively for the masses. Okay, corporations that produce just to distribute, to make money. No money, no incentive, no reason to produce food, and no distribution. And so what happens is the ecological pyramid overturns. Why does that depend on the population pyramid overturning? Well, because the fewer, in part, that's just one of the ingredients, right, in the recipe. And it goes like this, the fewer people we have, the less demand we have. And the less demand we have, the fewer things that big corporations can sell, both goods and services. And if they sell less, there's attrition. There's an implosion of the economy. Okay, so they lay off workers because they're not producing enough, because they're not selling enough. And that's a cycle that just keeps rolling and rolling until you have a collapse. And I say that process is going to be exponential. Just like it was exponential in the 19th century going up, when we industrialized essentially, this is going to be the same thing but going down. And it's probably going to be steeper. That's my guess on that. Okay. Let's move on here. So I don't think it's going to be corruption, by the way. Corruption is, it's just, yeah, it's in man. Man will try to do the utmost to become rich in general terms. And in order to do so, they don't care how they're going to do it. So corruption is part of the deal. It's part of history. It's been there all along, like this fellow says. But it's not corruption that's going to cause the extinction of man. It's going to be the overturning first of the population pyramid, followed by the overturning of the ecological pyramid, our food pyramid. Okay. Okay, another fellow says here, patriarchal groups that live in cities have a high birth rate, which proves this urbanization myth to be false, which is what I'm suggesting, okay? So I'm saying that all animals don't have patriarchal structures, yet they have offspring. So you got to have a universal, and right now you're only talking about man. You're not talking about all animals. So you got to do a research on all animals, and there you see something, how the fruits are attacked by something that's alive, and that living thing grows to a certain point, and then no more. Then as their world collapses underneath their feet, so to speak, right? They cannot continue reproducing and reproducing and reproducing, just expanding. No, they fall together with what's underneath them, what they're relying upon for sustenance. And that means that, that's what we call density dependent there. Density dependent birth rates, okay? You can't continue expanding forever if what you're relying upon is declining. And that's what he's got to understand as well. All species follow Mother Nature's law of density-dependent birth rates. Okay, and here you see here's for humans, right? The global history. Okay, and here it goes. Starts here in a second. It starts with the year, I think, at the beginning of the Christian era. Yeah, year 0, then 1,000 years. Shows you what's happening with the world. It just continues becoming populated, but see, there are regions that are not populated there, okay? And then in 2050, there will be no humans, okay? I'm saying that we're dead by the year 2050. There may be some human here and there, but it's not going to restart the race again, okay? The species. And so I moved the other day, I showed the other day this, which is what the world looks like today. And what you see there is all the regions, the major regions that have very little population. See, the way we're set up today, the way we're distributed population-wise, is in big cities. You have cities like Tokyo, which are close to 40 million people. I mean, what is it? And I think that's with a greater Tokyo. But the point is, people go to the cities today. They abandon the countryside and they go to the cities. And so we're not creating new towns, new villages. We're not creating new cities. What we're doing is evacuating the countryside, leaving that land to the big corporations, agricultural corporations, and we are moving in what is known as the transition to the cities. So the cities are becoming bigger, and when you have these big antholes, then density-dependent birth rates take place for cultural, economic, and social reasons. Okay, so there's several reasons for why we don't have children in the cities, and it's got nothing to do with patriarchal. Not specifically with patriarchal. It's got to do with density-dependent birth rates. And again, the higher the density, the fewer children you're going to find eventually. Okay? Tokyo is a prime example. Japanese don't have children anymore. Neither do Russians. Why? Because Russians have what? 2 or 3 cities. That's it. That's all they have. Mega cities, Moscow, St. Petersburg, Stalingrad, as it was called. That's it. All these, Russia does not have many cities. It has a few cities that are big, and everybody's moving to those cities from the regions around there. And so if anything, we're evacuating the countryside, not building villages and towns in the countryside. It's the other way around. We're evacuating those. Okay, so in fact, a lot of the old people live in towns, and as they die, nobody replaces them because there are no industries going to the little towns. The industries are getting closer on the periphery of the big cities, if anything, but never do they go into a little town and say, oh, we're going to install our big company here. No, it doesn't really happen today because all these corporations really, what they're doing is moving to the cities where the action is and where certain services are available. You can't go to a little town where there are no services or it's many things are missing that a corporation might need. They're not going to go to a little town because if they did, then the young people might flock there and grow with the city with the town. But that doesn't happen anymore. We're not going to the towns, we're going to the cities. It's the other way around. Okay? Anyways, I encourage people to do Extinction 101 before they do Extinction 102, meaning you want to do mass extinction first. Very few people tackle mass extinction. They want to do human extinction. Everybody's an expert at human extinction. I have yet to find people who are experts in mass extinctions that occurred already, which is what a theory is supposed to explain. You have to explain how the animals in the past died, disappeared, okay? And so that's the first one you got to tackle. Then once you become an expert at mass extinction, well, then you can extrapolate those mechanisms, see if humans, can do something about those as well. And the big question I put out there for anyone who wants to tackle it, and it's related to this again, and it's this, if I can get it up there. I've lost it. Anyways, the question is, why did the animals in the seas die approximately at the same time as the animals on land? Because that's happened in all essentially mass extinctions. When the animal on land died, more or less the ones who were flying died, and more or less the ones who were in the waters died almost or approximately at the same time. And you have to ask, why is that the case? Why did these animals die approximately at the same time? Because that might give you a clue as to how Mother Nature does extinction. Okay? So keep that in mind. Okay, so let's get on with tunneling today. Well, we've been dealing with several properties that quantum mechanics claims they've observed. Whatever observed means. Does observe mean with two eyes, like observe like I observed the girl who was taking off her clothes? No, nothing like that, okay? No, when they say observe, they mean they infer. But they say observe so that people listen, observe, and they say, oh, they saw it with their two eyes. And so if they saw it with their two eyes, who's going to deny it? Here you have all the so-called scientists, and they say, we observed. You're going to question that? I mean, you're going to say you need to go to the lab when all these people are telling you the same thing, that they observed something in the lab? But it turns out that the so-called observation is not an observation. It's not with the two eyes. What they observed was the visible things. What they touched was the tangible things. Okay, and tangible things are typically not anything atom or below. It's usually atom or above. And atom, that's a question also. Okay, they touch many atoms. I can touch a chair, which is gazillions of atoms, yeah, but I can't touch one atom, or I wouldn't know if I did. And so you got to keep that in mind. These people use the word observe, and that's why I hate the word observe in science. It shouldn't be there. First, because we don't do observations, and second, because we cannot observe that which is intangible and invisible. Mother Nature's mediators for gravity, magnetism, workings of the atom, light, etc., they're all invisible and intangible. So we're not going to detect them through a lab experiment, and we haven't in the last 10,000 years. No one has been able to determine what Mother Nature uses because it's invisible and intangible, and you're not going to figure out by running an experiment. You can run all the experiments you want. You won't be able to touch or see that which is invisible and intangible. And so the only way to look at this is step back and find out how Mother Nature could be doing this magic trick. And I give the example always, you see this guy going like this, and a box goes up. Okay? And it turns out, the box is attached to the rope. Rope is attached around the pulley, and the guy's pulling on a pulley, on the rope through the pulley. But the question is, if you didn't see the rope, and the guy was doing this, and the box goes up, are you going to say it's just black magic? Or are you going to assume that there is something that you simply can't see that the guy is pulling on? And that's the same situation here. We can't see light. Does that mean there is no mediator for light because you can't see or touch it? You put your laser and you put your hand right through it. And you're not hitting atoms or anything, you're not hitting the things that, colliding against the thing that makes up light. Your hand goes right through that. Does that mean there's nothing there? There's no physical object there? Okay? And so the question is, if it's intangible and invisible, of course you're going to run your hand right through the laser beam, whatever entity is there, and you're going to say there's nothing there because I can't see or touch it. And so you got a problem because Mother Nature has made specifically that mediator invisible and intangible. And until you get that through your thick skull, you're going to be running around in circles and running experiments and saying, oh, I'm going to run another experiment, see if I can detect it. You'll never be able to detect it. There's only one way, and that's sitting back and visualizing how Mother Nature could be doing all these things with some object which is invisible and intangible. So again, what quantum mechanics does is they found all these properties, all these phenomena, and what they do is describe the phenomena they observed or did not observe, and they have no idea what is mediating that phenomena. That's where we're at today. Okay, that's what quantum mechanics and essentially all of mathematical physics is all about. And so here's the recap that of what I've been talking about lately, and that's these properties that quantum supposedly discovered. Okay, these are things that they saw observed in the lab. What did they observe? Well, they say they observed decoherence. Well, what do we mean by that? Did they see an object do what is known as decoherence, which is a phenomena, a process, a verb? Have they found the noun that does decoherence? Have they found the mechanism, how Mother Nature does this magic trick? And the answer is absolutely not. They have not. So here's a decoherence. I call it incoherence. Okay, and you see the Slit Experiment, and they say that this particle, because they do everything, they simulate everything with particles, says the particle goes through both slits. And why is that the case? Well, they say if the slits weren't there, there would be coherence between these two. Essentially, they show them as particles, but they're going to turn them into waves. They're going to say that these two waves are in phase. But it's because something gets in the way and they interact with their environment that it becomes incoherent. In other words, it's coherent until it interacts with the environment. That's what these people are saying. Okay. And so, with that, we still don't know how Mother Nature does it. All they're saying is, if there's something there and it interacts with that something, it becomes incoherent. Until then, it was coherent, but as soon as it interacts, in fact, with your vision or your touching, then it becomes incoherent. You can't predict what's going to happen, or there's interference of some kind. So so they're not telling you how it works, how the magic works. They're just saying, we observed, right? Something happened, and we're going to call that decoherence, and we're going to use it for technology. We don't know what it is. We don't know how to explain it. We don't care about that. We're just going to use it because we found this effect. That's what they're saying. Entanglement, no different. What is entanglement? Well, it says that what you have, here, let me get this up here. Entanglement means that one particle here can affect another one over there without a mediator, without anything between them. Now, what sense does that make? How can a particle affect that one over there without any mediator? And they just say that it does. Okay, so it does. I'll concede, I'll grant. how does it do it? How can we make sense of that? And the answer is, it is so. That's what they say. Well, that's only a description, and we don't have an explanation. And they say, well, we can use it for technology. Again, it's all this stuff about technology, which is confused with science. Science, we have to explain how it does. How does Mother Nature does this trick? Not just describe and say it happens. Yeah, we notice that when they move this over here, that one moves over there in some certain way. Like in this case, I'm showing we have counterclockwise here and clockwise over there, and then when you turn one of them around, the other one turns around instantaneously. That's what they found. In fact, that's not what they found. What they really do is they have polarizers where they check the orientation at that location. So it's kind of like a static experiment. It's not something where you're seeing really motion at the cross section where you put the polarizer. Okay, so keep that in mind. Okay, I used an ellipsometer when I was in the semiconductor industry, and that's essentially how they do these things. They do it using an ellipsometer. Okay, next one, superposition. That's another one that I covered. Okay, what is superposition? Well, it says that while the horse gallops, it also stands still. What sense can that possibly make? How can something be standing still and moving at the same time? And they say, yeah, a particle can vibrate and not vibrate at the same time. It's excited and not excited at the same time. What sense can you make of that? Does that make any sense to you? I mean, if it does, well, maybe I'm wrong. I don't know. But I'm saying that's nonsense. It's called poppycock. It's idiocy, irrationality. Use any of those words, you're fine. Schrödinger's cat, the cat is both dead and alive. What can that possibly mean? How can a cat be both dead and alive? And what they use for that is two features. They use complementarity and uncertainty. And here you see the cat is alive and dead, both, until you open the box and you peek inside. Then it suddenly collapses to one of the two states. And again, they use all these observations, as they call them, these phenomena, superposition. They use decoherence, complementarity, uncertainty. They use all those. They mix them up, put them in, bunch them into one. They say we observed each one of these phenomena. And here's complementarity. Okay, the next one there. Niels Bohr's complementarity. What does that mean? Well, it's duality. It's something they love. They love all these dualities. Light is both a particle and a wave. That's what good old Niels says. So you see the particles that are rolling, the yellow ones, and so light is both particles and waves. Waves being a bunch of vectors only. Particles, I don't know how you can get them to move up and down because it's got to be oscillating. So we can't reconcile particles with waves, but they say light is both particles and waves. And so what sense can you make of that? Well, what does that mean? And again, they say, well, we don't understand that. We don't care because we're going to use it for technology. And as long as they find some use for the effect, they're happy because they say the rest is philosophy. We're never going to figure this out. And we can't figure it out. Why? I'll tell you why they can't figure it out. Because they're using particles. You cannot explain this with particles and with one-way mechanisms, which is, what you see there. Both waves and particles are outgoing. They allegedly come out of the atom. The atom produces the waves. The atom produces the particles, whichever or both, and shoots them outwards. Okay? And under the rope model, it's a bidirectional mechanism. So it's a lot different than this. There is no such thing as a wave, first of all, because again, those are a bunch of vectors. That's all we're seeing, moving vectors. What is vector? Magnitude and direction. Okay, so what is that? Mathematics, that's what it is. Okay, and here you have uncertainty. Okay, showed this the other day also. Here's Mr. Heisenberg and his uncertainty principle. And what is he saying? Well, he says that, the ball bounces at the same time that it stands still. And see, they're all related, all this uncertainty, complementarity, together with decoherence and superposition. They have all these concepts all together from different angles. And they put them together to try to give you an explanation. What's the explanation? An irrationality. They give you something which is absolute nonsense, which is duality, that it has two aspects which are contradictory, which are irreconcilable. Motion and standing still, location. And that's what you have there. The ball stands still, it also moves. And so this is the uncertainty principle. If you think that's going to make your life any better, well, they say they can use it in technology. Well, we don't care if they can use it in technology if they cannot explain what's causing it, if they cannot make sense of that. And right now we have a problem because we're reaching the end of the line where, they've had this for 100 years now. Quantum's been around for 100 years, and they cannot explain any of this. And here, they're at the same starting point as they were in 1926, 1927, when they started concocting all this so-called theory of quantum mechanics. Today, we've made no progress whatsoever. They have no explanation for any of this. All they have is more equations for different aspects of this, and that's all they have. And right now, they've kind of painted themselves into a corner because they still cannot give you an explanation for this. And they've abandoned that. It's like Richard Feynman says, they've given up on that. So they don't have an explanation. He said that in 65. And here we're 40 years, 50 years down the road. They still have no explanation for this. And so what more are they going to do? You think they're going to find a solution to this? And the answer is no. And the reason they cannot find a solution is they're dealing with particles. Mother Nature cannot be using particles. This was the time to wipe the board completely clean and start all over and brainstorm some new mediators. We can't continue using particles or waves. That's the issue. And fields, it's not a physical object. Field is a mathematical concept that is of value at each point in space. That's all a so-called field is. So there is no such thing as a field. There's no such thing as a wave. And particles, right now we're not even using particles. We're not using the classical corpuscle. What we're using is zero-dimensional equations. That's what a particle is, an equation. That's all it is, a function. Okay, and spin, which we dealt with the other day, here it is. Okay, and that means that the dancer spins both ways, okay, clockwise and counterclockwise, until you, again, see or touch him. As soon as you see or touch him, he collapses to one or both, to one of the two states. Okay, meanwhile, he goes clockwise and counterclockwise. That's what they're saying spin is. And it turns out spin is not even spin. Spin is a static concept. It has to do more with orientation. But as we explained the other day, if they use the true spin, first of all, it doesn't match what they observe in the lab, in the effects they observe. And second, they cannot explain attraction with that anyways. So what if an electron spins? How does this electron from this atom over here attract that electron from that atom over there? How do you produce attraction with two little balls? Spin them any way you want them. Okay, spin the tops, one clockwise, the other one counterclockwise, spin them both clockwise, spin them both counterclockwise, it doesn't matter. One top will not attract the other top. So at some point, you got to put an elongated mediator between objects, atoms, right? In order to be able to explain how Mother Nature does her things. Then you can explain action at a distance. And the only assumption you have to make is you can't see or touch that mediator. Why? Because that's not what an object is. An object is that which has shape. Okay? So yeah, as long as you insist on see, touch, and doing experiments, then you're in trouble. You'll never answer the question. Okay. Here's tunneling, which is the next phenomenon. We've seen all these other ones. This is another crazy phenomenon of quantum mechanics. Okay, and it goes more or less like this. You have a snowball, big ball, okay, and it hits this mountain and it bounces backwards. Okay, that's what we would expect for a snowball to do. Okay, it hits the mountain, bounces back. Okay, no problem there. So far, so good. Okay, what they say is, why can't that ball go up the mountain and climb over it and go to the other side? Okay, and so here, let's show that. Okay, it's going to try to do that. Going to try to climb, 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 and it doesn't have the energy, whatever that is, to reach the top and go over the side of the mountain. Okay, so what happens is they cannot explain if they were to find the snowball on the other side. That would be a miracle, right? There's no way it can happen, at least in classical mechanics. You would need so much energy to get up that mountain that that's not what they observe in the lab. Okay, so what is it that they observe in the lab? Well, what they observe in the lab is this. Okay, they observe that the ball is on the other side. Okay, so now how do you explain that? Turns out this ball was rolling along. It didn't climb the mountain. It just went through it. And they call that tunneling. It's like it went through a tunnel, like if the mountain had a tunnel in between it. And so, yeah, now we have a problem because we have to explain that. What do you mean it's got a tunnel? What is that? And the way they explain it is more or less like this. So hold on to your seats right now because this is just going to drop you flat face down on the floor. Okay, here it is. What they say is the reason the snowball ends up on the other side of the mountain is it rolls and the snowball turns into a wave. It just goes as a wave through the mountain and then it arrives at the other side. Now, ain't that neat? Man, I wish I would have thought of that. That's the best explanation you can have, right? Or is it? I mean, don't you call that black magic? I mean, not even the Bible has this kind of stuff. This is really ridiculous. They're saying that the ball turns into a wave and that's how it ends up on the other side. Okay, and you say, okay, doesn't make any sense, but okay, what's the explanation for this? I mean, are they just going to say it is so? Well, more or less, that is what they say, okay? They say that the ball rolls, turns, as soon as it hits against the wall, you have this interaction, right? Kind of like the decoherent stuff that it interacts now with its environment because it hits something, and now it's going to act a little differently, okay? And so you say, well, what is the explanation for this? And here's a nice, fine young lady who explains it for us. I assume she has a degree. I haven't really looked into her past, but she has a YouTube channel. She tries to explain it. And this is what she explains, okay? And she explains that she knows nothing, that she has no clue, okay? Here it is. Her name is Jade Tan Holmes, and she's a cute little girl. That's great, but here we do science. We don't do beauty. You want to do beauty passion, pageants? Well, you got to go somewhere else. So she says, it may seem stalling that we're treating the wave function exactly like an electromagnetic wave, whatever that is, because you treat a wave function as a wave, you haven't made much progress. They're both concepts, they're both verbs. A function is an equation and a wave is an equation also. There is no such thing as a wave. Wave is a bunch of vectors that are moving somehow because they make them move in mathematical physics. She says it's hard to imagine something so abstract like the probabilities of electron locations as a real physical thing that travels and reflects and tunnels. Yeah, it is. It doesn't strike her. I mean, it doesn't snap her out of it, that hypnotism, that something is wrong. Are we just going to accept this and bow down and say yes to the professor because he's going to be the supervisor of my thesis? The truth is, scientists still don't know exactly what a wave function is. They don't know what a wave function is. Well, I'll tell you what it is, lady. A function is an equation. That's all it is. It's a bunch of numbers or a bunch of letters that represent numbers, etc. So yeah, we do know what a wave function is. It's got nothing to do with physics. Physics deals with objects, and this is math. That's what it is. They don't know whether it's purely a mathematical tool we've created to help us predict things about quantum objects, or whether it's a real physical wave. My God, poor girl. I mean, it is a mathematical tool. Hopefully, wave function only has to do with math, but it turns out the wave also has only to do with math. There is no such thing as a physical wave because you have to identify what it is that's waving. You know, when you do the simulation in front of the class in college, well, you take a string and you move it up and down. Got one here? Yeah, maybe here. Something like this, okay? I hope you can see that. It's a very thin black wire. Okay? And when they do that, okay, why can you see the wave? Well, because they put a physical object, in this case, some kind of thread, some entity, elongated entity. Then you can wave it up and down and you can talk about wave because what's waving is the string, the thread, the rope, whatever you're using. But there is no such thing as a wave without a physical mediator. And she's talking about a real physical wave. Oh, what's the wave made of? What is this wave? Are we talking about a string, a rope? What is this wave? And she thinks it's a real physical thing. That's what she learned by rote in college in order to get her degree. And now she goes on YouTube and just peddles the same thing she memorized by heart for the test. Is this science? Or is it poetry where you just recite what you learned by rote? But what they do know, this is what they know. We know. I don't think I know. I don't think you know either. What they do know is that it can be modeled pretty much perfectly by wave mechanics. Well, I don't care if they can be modeled by wave mechanics if that's an equation. That's what she's talking about. Again, we're missing the object. We don't know what's waving, what physical object is doing the waving. And so she hasn't explained anything. And you wonder, why is she on YouTube? And she does a lot of videos just like so many others out there where they supposedly go in there and say, oh, I can explain how quantum works, or let me tell you a little bit about relativity or string theory. And what they do is they repeat over and over again for the last 50 years the same old stuff. She hasn't contributed anything new. And you say, Bill, aren't you being a little harsh on this girl? I mean, she's just trying to make a living, going on YouTube, etc. No, we have to embarrass these people. There's so many of them. They're crowding out the internet, they're crowding out YouTube, they're crowding out so many other platforms out there. And all they do is repeat the same thing that the other guy next door said. It used to be that we needed a teacher in every class. If these people are going to be doing teaching, on YouTube, all we need is one teacher for the entire world. Everybody can tune in to that teacher from any part of the world and learn the same thing. We don't need the same material being given by, thousands of different people. Now you might say, well, maybe I like the way this person says it instead of that one. Yeah, fine. How many versions do we have for quantum? How many versions do we have for general relativity? How many versions do we have for string theory? Do we need, let's assume we have 10 versions of quantum mechanics, different ways of explaining something. Do we need any more? We have thousands of these people on the internet. What are they there for? To say the same thing as the guy next door said? To say the same thing they all learned by rote in college without providing anything new, without giving you an explanation, instead of all they give you is a description, mathematical description said in English, in regular language, in vernacular. So they give you this presentation. They say, look, this is what the mathematicians mean, and this is how I translate it for you people who are laymen, okay? Or lazy men. And so they give you this version, and they're all giving you the same version. Maybe the guy focuses it a little different than the other guy. Again, with 10 people, we should cover the whole planet. We don't need more than 10 people on YouTube explaining the same thing over and over and over again. And what we have is thousands of people because they're out of work, and they say, look, I got my degree. Should I go and look for a job at a company? No, this girl says, well, I'm kind of cute. I think I can go on the YouTube and make some money just spreading the same thing that all the other guys do. You know, if she's cuter than the gal next door, well, maybe they'll watch her instead of watch the other lady. Is that what science is about? And this is all we have today. All we have is these people just crowding out the internet, getting thousands of votes, lots of ups. Everybody likes them, you know, say, oh, I like it. What do they learn? They learn the same nonsense that they're going to learn from anybody else, and they all say the same exact thing. And we haven't made any inroads in 100 years. Not one of these people can explain to you, like she says right there. They don't know. They don't know, they don't know, they don't know. All they know is that it works, that they saw an effect, and they can use that effect because it works. They can use it in some kind of technology. And they say that's as far as we can go. And they call that science. Okay? So yeah, we don't have an explanation today for any of the things these people do. Okay, so here's the moving vectors that I was talking about. Okay, this is, let me get this one out of the way here. What you're seeing there is a moving vectors. Okay, this is what they're saying that they're seeing, or that's what they're imagining, because they don't see this. They're imagining that this is what's in that invisible world. But what are you staring at? You're staring at a bunch of vectors. What are those arrows? They're just vectors, mathematical vectors. What is that? Magnitude and direction. And you have magnitude and direction, which is moving. That's what you're staring at. So yeah, these people have no explanations for that invisible world of quantum mechanics. And the main reason for that is you cannot see or touch the mediators of gravity, of light, of magnetism. You can't see or touch them. You can only visualize them, you know, close your eyes and try to imagine how Mother Nature could be doing this process, what the mechanism that she's using in that world. And hopefully you do it with objects, because otherwise you're introducing black magic. So you have to have an object. What is an object? Is that which you can see and touch? No, it's that which has form, which has shape. Okay, so what are my conclusions for all these effects, these quantum effects? Well, here it is. Conclusions. Quantum fails to explain the key mechanism. What are they? Decoherence is irrational. Entanglement, they cannot explain. It's irrational. Superposition, also irrational. Schrodinger's cat being dead and alive at the same time, irrational. Until you observe, until you peek inside the box. Complementarity, duality, that light is both a particle and a wave, irrational. Uncertainty, that the ball stands still at the same time it moves, and when it moves it doesn't stand still, when it stands still it doesn't move. Well, that's quite rational. It's just incredible that they needed an equation to explain that, which, you know, any kindergartner could have told you. Okay. Spin, irrational. Why? Because it's not spin. And even if it were spin, you cannot explain attraction, action at a distance attraction, with two tops that are spinning. How does one top affect another top? I don't care how they're spinning. So it's irrational because the mechanism, the fact that it spins, even if it did spin, which it doesn't, but even if it did spin, you cannot produce pull, which is the only force missing in quantum mechanics. Tunneling. Tunneling is irrational. Why? Because they convert the ball into a wave. They convert the photon or the electron into a wave. They say it's got both features. It's both a particle and a wave, and they go back and forth because that's the only way they can get it through the mountain, the ball through the mountain. And no problem. I'll even concede all that. I just need the process. I need to know the mechanism by which a particle converts into a wave and a wave back to a particle when it's on the other side of the mountain. Now, how's that for an explanation? That's what we need. We need an explanation. If you don't have an explanation, then all you're doing is black magic. All you're saying is, it is so. It is so. I haven't learned anything because you're telling me that, you know, one thing converts by magic into the other. What's different than that than saying that Jesus Christ went to heaven, came back, and then went back again, I guess, right? Back and forth. And you say, well, that's superstition. Well, what is this? What is this nonsense? Is it, I mean, what do you want to call this? Superstition? You can call it, instead of superposition, superstition is probably a better word. It's nonsense. This is poppycock. This is idiocy. And we've been living with this now for almost 100 years. Not all of them at the same time. They discovered these phenomena as time went by, but this is what we have today. This is the summary. Okay, corollary. No wonder Bohr, Heisenberg, Feynman, among others, everybody else in quantum, candidly state that no one understands quantum mechanics. No kidding. Okay, folks, let's get to the questions and comments that people made. We have a few of those. Let's go with the first one here. One fellow says, squares have shapes, so then where are they? Where are they? They're here. They're in your mind. They're in your brain. Okay, that's where they are. If they don't have location, they are not objects. Well, for that, you have to define the word object in such a way that you can use it consistently. Okay? And objects are that which have location and shape. Light doesn't have shape. Light doesn't have shape. Prove that light is a torque. Poor fellow. Okay, let's show. First, we must define the word object before we define the word location in physics. See, you can't define location before object because what's at the location? Okay, you need an object at a location. Otherwise, there is no such thing as location. Okay, and so first you got to define location before you define object. Therefore, no, the word object is not shape and location. Okay, it can't be. Can't be both because location has to be defined afterwards. Nevertheless, once you define location, object plus location, that's what the definition of exist is. And object and exist are not synonyms, which is what this fellow believes, which is what, David Hume and Immanuel Kant essentially believed, that there was no difference between the word object and the word exist. And yes, there is. There's a difference, and that is the word location. An object with location exists. An object that does not have location does not exist. What are those objects that don't have locations? Well, they're imaginary objects, the ones that you think about, that you can imagine, that you can visualize. It's also 2D objects. They have no location. What has location is the ink, the paper, the screen, the pixel maybe, those have location. But the Superman on that screen or on that piece of paper, Superman is an object, it has shape, but Superman does not exist. Okay, so it has no location. The word rock is always an object. Okay, no matter where. So are you going to say that rock is not an object because you have a rock that does not have location? You have a rock that you're imagining. You have a two-dimensional rock scribbled or drawn on a piece of paper. So that you call it rock and you're saying that's not an object even though it has shape. Okay, just because it doesn't have location. So no, the word rock, the word table, the word chair, all these tree, all these are objects anywhere in the universe. The word rock belongs to the set of objects, always. Whether it's imaginary, 2D, or 3D, or existing, or whatever, it doesn't matter. Light is mediated by an object, and there you see it. Right at the bottom, okay? In the classical mechanics, you have one-way mechanisms, only one way. It could be, particles, corpuscles, or it could be waves, which is not a physical object, but even assuming it's a physical object, it's one way. And then quantum mechanics has those same two, but again, they turn the particles into not corpuscles, but essentially they're nothing. They're equations, they're formulas, that's all they are. And what they've done is they blended the two in what is known as the wave packet. That's, what's his name? Roger Penrose's squirrely wave packet there. A little curlicue with an arrow through it, but is also one way, okay? Rope hypothesis is the only one that is a two-way. First, it's a physical object because it has shape. We're talking about a rope-like mechanism, looks like DNA, if that helps you visualize it. And it's a two-way mechanism because it torques. And torsion goes both ways. And torsion is also the fastest thing known to man. Okay, there's nothing faster than a torsion wave, if that's what you want to call it, a three-dimensional torsion wave. Okay, next issue, fellow says, or asks, says, ropes of what? Threads of what? There is no such thing as an electron. It is a mathematical concept. Okay, let's look at the threads of what question there. Okay, let's find out. Okay, what he's doing is mereology. Asking, what is an elephant? Well, an elephant is what it's made of. An elephant is gazillions of atoms. Well, for that matter, so is a bear, so is a table, so is a tree. They're all gazillions of atoms. So is that how you're going to define it, by how many atoms it's got, what it's made of? It's known as mereology, and we don't deal with mereology in science. That belongs strictly to religion, what the standard, what is it, Stanford Dictionary of Philosophy does. You know, these philosophers, they do this kind of stuff, mereology. It's religion. It's got nothing to do with science at all. It's just nonsense. It's what an object is made of. We don't deal with that. Elementary and fundamental entity, that's what we're talking about here. And so you can't say, what is a rope made of? Rope is made of two threads. Very easy. I mean, here it is. Okay, here's my rope, my famous rope. Okay. Two threads, two strings, two whatevers you want to call it. It's even two ropes tied around. Okay, so what is a rope made of? Two whatever threads, whatever you want to put in there. Two cords, two cables, two wires. Now you say, what is the thread made of? The thread is not made of anything. It's a fundamental entity. And only irrational people continue asking, well, what is it made of? Well, if you ask that question, it means you didn't understand what an elementary entity, what a fundamental entity is. A fundamental, elementary entity. Get this right, okay, in your tiny brain, okay? A fundamental entity is one that is not made of anything. The buck stops there. You can't continue saying, like the quantum mechanics do to create job security. They say, well, we found this particle, okay? We'll call it the alpha particle. Okay, what is the alpha particle made of? And they say, well, give us some money and we'll break it up into pieces with these super colliders. Okay, they go in the lab, they break it up, they say, oh, we found these traces there, and we found that the alpha particle is made of gazillions of beta particles. We could peer deeper. We broke that particle up, now it's made of all these little chunks, and we'll call them beta particles. Okay, great. So now the reporter at the end of the room said, what is the beta particle made out of? And the mechanic said, well, it's a fundamental particle. What does that mean? Well, so far, as of today, we don't know what it's made of. So you don't have an answer for us? Well, yeah, I'll have an answer. If you give me more money, I'll build even a super collider, one as big as the moon or as big as the orbit of Jupiter. I'll smash the beta particle and I'll tell you what it's made of. And so they give them money, they build the collider, they smash the beta particle, and they say it's made out of gammas. And they just keep going on and on and on and on until, you know, finally the buck stops at some point because they don't have enough money to build a collider as big as, you know, the Milky Way galaxy. And they say, well, unfortunately, we don't have a collider big enough to smash them to tell you what it's made of, what gamma is made out of. So the way we do it in science is a little differently. We don't go to the lab and smash particles and then try to figure out what that particle is made out of. That's mereology. That's nonsense. What we do is define. We say an elementary or fundamental entity is one that is not made of anything, any sub part. It's not made of anything itself. It is the thing that comprises everything else. See, and quantum doesn't want to do that because it's the end of their reign. If they say, well, look, all particles are made of, I don't know, gammas. Okay, so all particles, the gluons, the Higgs, the quarks, the electrons, everything is made of gammas, whatever gammas is. And then the reporter asks, well, what is a gamma made of? And that's what this person's asking. Well, what is the fundamental entity made of? It's a fundamental entity. You got to start somewhere. You can't continue just going with a question and over and over and over and say, what is this made of? What is that made of? What is the other guy made of? That's mereology. In science, we say there's a fundamental entity that comprises everything else. That's where the buck stops. And that's known as the thread. Single thread that makes up all matter in the universe. Now we have a starting point. And you can't say, what is it made of? It's made out of thread. That's what it is. Thread is made of thread. That's what but quantum loves that, because, again, they don't look at objects. They don't look at things. They don't have any idea what the invisible, intangible things that Mother Nature uses. So they just put particles there. And they leave it at that, and they just work with particles. They simulate everything with particles. Whenever they can't, they use the wave, but generally it's the particle. They explain almost everything with particles. Why? Because they can put a value, which is what a particle really is, a value in an equation. But then they say, well, what is decoherence? Oh, we don't know. Well, what is entanglement? Oh, we don't know. How does that work? We don't have any idea. But they don't care about that because what they say, look, we observed the effect in the lab. Okay, they observed the effect in the lab. They don't know how it happened. They have no idea because they're going to try to do it with particles, and there ain't no particles out there. But they're going to explain it. They're going to simulate it with particles. Now they're going to use the effect where? In technology. And they say, oh, look, we have a quantum computer. Oh, why is it a quantum computer? I thought it was a classical because you build it with atoms, and atoms and above are classical, and everything that we can see and touch is classical, and you're saying this is a quantum computer. Yeah, because we're using the effect that we cannot explain, but that we observed, we tested it and saw that this effect repeats itself. Every time we do this, this is what happens, and we're going to use that what happens in the computer. So they have no idea. It's like saying, here's a magnet, and I can pick up iron filings. Okay, how did that happen? Oh, we have no idea. But look how neat it is. Every time we put a magnet, it lifts all these iron filings. And so they say, I can use this. I can lift cars with this at the record. The rec yard there. All these cars, I can get a magnet and pull them up. How does it do it? Oh, we have no idea. But look how neat it is. We can use the technology because we've observed the effect. And this is essentially what these people are doing. These people are saying, we can use the effect, and we'll call it a quantum effect. And then some people come to you and say, well, you wouldn't have that computer if it weren't for quantum. People who don't understand what the issues are. The issue is they saw an effect. They observed the effect. They observed the classical part of the effect, something that happened, the part they can see, measure, etc. And they're going to use that effect in a computer. They call it a quantum computer. Why? Is it because they built it out of parts small parts, subatomic particles that they understand and they know how they work? No, absolutely not. They only see the visible part, the tangible part. That's what they're going to put in a computer. And they're going to say, if we do this, this is what will happen. We don't know how or why, but it does happen. And they call that proof, evidence. And that's where they get the title or the adjective or the qualifier quantum computer, quantum dot or whatever. They have all these things. Why? Because they can get away with that. Okay? So yeah, that's the context for quantum mechanics. Okay, next question or comment. Person says, your thoughts on the next step in the rational method after you have two or more rational explanations for a single thing. Okay. Is that where it stops, or do we do religion and pick one rational explanation over another? Yeah, at that point you do religion. You can choose any theory you like. I was talking about the Neanderthal theory, the fact that they were born in Europe and they never went south. That's the one I like. That's the one I use as an assumption for my theories. Okay, so what became a theory now becomes a hypothesis, a starting point for a new theory. Okay, and you might say, well, I think something different. I think the Neanderthals came from Africa or from Asia or whatever, from America. American Indians were Neanderthal. After all, you know, they have more Neanderthal blood than Europeans. Remember, American Indians have more Neanderthal blood. So, you know, you can have any starting point you want. You can believe in any theory you want. But the issue is that belief has to do with religion. Assumption is a little different. Assumption, you're just going to assume the theory that someone got out there is true, and you're going to use it as a foundation for another theory. Okay, and someone can challenge that and say, well, I don't agree with your assumption. Okay, fine. But because of this, this, and this, you can criticize it. But the issue here is that that's the way science works. Belief is something different. Belief is religion. Knowledge, when you know something, you've got a religion. Okay, that's known as religion. What is knowledge? Justified true belief. So said Mr. Plato. Okay, another fellow brings up good old Kenny Wheeler. Okay, he says, by the one and only Ken Wheeler. I guess he's a follower of Mr. Wheeler. Okay, and what does Wheeler say? He says, counter space, also accurately called the ether realm. Whoa, the ether realm. 0 point energy, whatever that is, or simply the ether, whatever that is, the realm of pure potential, whatever that is, okay, or unmanifest energy of which, by which, and from which nothing is possible or even theoretically potential without same. I don't know what he said. Okay. Counter space is the null point opposite of Cartesian forms, masses, magnitudes, and phenomena. Okay, great. So far we have nothing. Okay. There are only 2 dimensions in nature. Oh, okay. We have length, width, and height? No. Maybe just length, width, maybe width and height? No. He says there's only 2, spatial and counterspatial. Okay, that's counter space. Okay. Counter space for me is, you know, how much space I have for my beer on the counter, in the bar. But they have some other idea for counter space. Okay, says counter space is the null point opposite of Cartesian. Okay, there are only 2 dimensions in nature, to more accurately dimensional and non-dimensional. Okay, so it's a yin and a yang. Either you have dimensions or you don't. In dimension, there's only 1 dimension because the other one is non-dimensional, meaning so you have a 0 dimension and a 1 dimension. So there are not 2 dimensions, there's only 1 dimension. Okay, whatever. Anyways, he wrote a paper. Yeah, I encourage you to look into it. Okay, it's Definitions of Nature and its Phenomena with a primer on cosmology and ontology. Oh my God, must be important. He gets this stuff from a book that Mr. Wheeler published, which is this one, Uncovering the Missing Secrets of Magnetism. And you can look this book up. It's on the internet. Mr. Wheeler has made it downloadable, free, okay, free of charge, so you can just go in there and look at it. And the only thing I'm going to say about that book is that I challenge anyone, I'll buy a beer to anyone who can understand it. And I'm not asking you to read the whole book. Please, you'll be tortured. It's not that it's not well written. I've never seen a book that I cannot read, and that's Mr. Wheeler's book. You cannot read it. It's unreadable. I'm not talking about poorly written. I've seen a lot of stuff that's poorly written. His is not poorly written. You cannot possibly understand it. It's impossible to understand. Just like his videos, a lot of them, you know, most of them really, you cannot understand what he's talking about. Why? Because he throws a lot of words around that he's just to show off that he knows how to pronounce them. That's about it. Because he never defines them. He doesn't define them in any of these 2 books. And, you know, so again, I encourage you to look those books up. And again, I'll buy you a beer if you can understand it. I promise. I'll buy you a beer. Okay. Okay. Another fella here says, this comes also from Wheeler's book. And listen to this. This is interesting and important because Wheeler mentions Newton. He mentions him second. He should have mentioned Newton first, but it doesn't matter really, because he's going to mention Newton and he's going to invoke also James Maxwell. And this is what he says for Newton, that Newton said this. And again, he doesn't include the actual words that Newton said. And again, it shows that he doesn't do any research. He doesn't go in there and look at the original sources. He wrote something which is not what Newton said verbatim, okay? And there's a difference. But let's just go with, I pulled up the actual one that Newton had in his letter to Bentley. And that's the unconceivable, listen to this, okay? That inanimate brute matter should, without the mediation of something else which is not material, operate upon and affect other matter without mutual contact, that one body may act upon another at a distance through a vacuum without the mediation of anything else by and through which their action or force be conveyed from one to another, is to me so great an absurdity. And he kept going, okay? He's saying you need a mediator, a physical mediator. He cannot figure out what, but he says you need a mediator. Otherwise, it doesn't make any sense. That's what Newton's saying. And he says gravity must be caused by an agent acting constantly. Newton said this, okay? Okay, that's Newton. Okay, here we have Maxwell. He comes in a few centuries later, but he says something along the same lines. And this, again, this quote comes from this fellow Curly, what's his name? Ken Wheeler. He says, Maxwell says, there appears to be in the minds of these eminent men some prejudice or a priori objection against the hypothesis of a medium in which the phenomena of radiation of light and heat and the electric action at a distance take place. The existence of a medium in which light is propagated. Okay? He's talking about a medium. He's talking about an entity, something that's got to be in there. Whenever energy is transmitted from one body to another in time, there must be a medium or substance in which the energy exists after it leaves one body before it reaches the other. Okay, so here we have two researchers, a little old now, but they both said or came to the same conclusions. Okay, and that's what Wheeler is trying to say here. Okay, and let me get these two fellows out of here for a second. So what does Wheeler say? Because he brings these two, he quotes these two gentlemen, Mr. Newton, Mr. Maxwell. He quotes them like saying, see, you got to follow these guys, okay? Okay, let's see if Mr. Wheeler follows them. What does Wheeler say? And he says this right immediately after, right? He says the following, and this is Mr. Wheeler there. He's always an angry Buddhist, an angry monk. Says the single greatest fear you can instill in any materialist, okay? So he doesn't agree with materialists, even though, what did we just hear from Newton and James Maxwell, that you need material, something, you need a substance, you need a thing there, but he's going to criticize materialists, is to ask him to define a field, okay? Atomic operations are mediated by and through a field. Oh, I thought a field was a bunch of numbers. That's not a physical entity. That's not material. That's not what Newton and Maxwell were talking about. They were talking about a physical entity. A field is not a physical entity. Field is defined as a bunch of numbers. So yes, materialists know what a field is. It's a bunch of numbers. It's a bunch of values around the center point and declining the further away you get from it in strength. So that's all it is. A field is a bunch of numbers. That's all a field is. All fields are the ether. Okay, so ether is a bunch of numbers. I guess that's what he's saying, right? Because that's the definition of field until he defines it otherwise. Okay, so the definition of field that everybody uses out there, bunch of numbers. Okay, that's all it is. All fields are modalities of the ether without exception. Any conception of action at a distance without an ether field, redundant, but he says all ethers are fields, okay, but he says an ether field as mediator is illogical, senseless, and impossible. Well, a field is a bunch of numbers. That's not a physical mediator, so it's not a mediator, not for the purposes of physics. And so if Mr. Wheeler doesn't understand that, well, he's got a long ways to go. He's got a steep learning curve ahead of him, okay? Yeah, field is not a physical object. Sorry to inform you. Look up the word field. You'll find it's a definition, and the definition says that it's a bunch of values. That's all a field is. In fact, it's not a noun. You shouldn't say a field or the field, because that turns it into a physical object in physics. In science, we don't talk about fields like that. Only mathematical physicists talk like that. Okay. Anyways, you look up. He says all fields are ether. Okay, let's see what it says. Ether can with a or with ae, either way. So he's got ether. Okay, what is an ether? Ether is pure potential. Potential. That's a physical object. Potential. What the hell is a potential? Sounds like math. Non-Cartesian counterspatial inertia. Whatever that nonsense that is. Inertia means that you have resistance to push. That's what it is. So again, we're not talking about a physical object. We're talking about the effects here. The essence of all field modalities. Yeah, which means that field, inertia, potential, ether, all these words that he uses, none of them are physical objects. So he's trying to do, he quotes Newton, he quotes Maxwell, who talk about entities, and he's treating these as entities. In his mind, he thinks these are entities, things, objects, bodies, substances. Absolutely not. These are mathematical concepts, abstractions. You can't do pull with field. You can't do pull with wave. You can't do pull with inertia, modalities, or whatever, fields, whatever thing that, he's just using words, ether, he's just using words. And yeah, so-called indefinite diet or attribute of the absolute. He's just talking nonsense, absolute nonsense, poppycock. None of this has any value in physics whatsoever. And he's got a lot of followers. Obviously, people who say, "Oh, I understood." Yeah, come and explain it with objects. Okay, don't use counterspatial. Don't use field. Don't use any of those words. I want you to draw the physical mechanism of attraction. That's what I want you to do. Whether you do magnetism or gravity, do it with physical objects. I want to see what you draw. I want to see what you put your mechanism in motion. Show me the movie. Don't talk. Show me the movie. If you can do that, then you understood. You understood attraction. You understood action at a distance, effects. Otherwise, you don't. What are you going to do? Put a field? What are you going to draw for a field? Bunch of numbers? Okay, fellow asks, here it is. Are the threads of the magnets also connected to the ropes? And no, the answer is no. Threads are twined and are connected to atoms, not to ropes. Nothing is connected to the rope itself. If it were, we could see the ropes. Because imagine, here you have a rope, and imagine one perpendicular to that, attached to that. Then we would see the vibration coming along that rope to your eye, and you would see the rope. The reason we can't see the rope is we're looking along the rope, which is torquing. The torsion is light, but light is the sensing point. It's stimulating an atom, and that sensing, that stimulation of the atom, the fact that the atom is quantum jumping, then quantum jumps faster or slower, that's what we detect. It's the pumping of the atom that is light for our eyes. The mediator is the rope, but we don't see the rope itself. What we're detecting is the pumping of the atom at a given frequency. That's what we detect. We detect the atoms in that sense, not light itself. So no, the threads, you cannot see them. And again, there you see clockwise and counterclockwise how the threads attract and repel. The one on the left is attraction, and what you have is they're both going clockwise. So one is, when one comes down, the other one clips into it and pulls it, and the other one is they're hitting against each other, pushing each other away. Okay, so that's how the threads work. Now, the threads come out of the electron shells. They slide out when atoms are spinning at great speeds, which is what happens during electricity. So it spins perpendicular to the spin of the atoms, of the electrons essentially that form the atoms, right? The electron shells. And that's when the threads come out and they swing around. Okay, they swing around the row of atoms which are bound to each other, which are merged with each other. And so that's what's spinning. That's what the threads are doing. They're spinning around, and both threads spin. I think someone asked that question. Let me see here. Yeah, here it is. Fellow says, I have a question about the rope. Is there a qualitative difference between the electric thread and magnetic thread? The answer is no. Magnetic thread swings around wide. Could the electric thread be always straight? Originally, that was my idea some years ago, okay, and we changed that. I'm saying we because my son suggested maybe both of them come out, okay. They could come out of the rope or they could come out of the electron shells, okay, either way. But what you have is a single thread in the entire universe. There I show two threads because some people say, well, then it doesn't exist because it doesn't have locations, an object that doesn't have location with respect to another thread. So to quiet those people down, we put two threads because there could be a parallel universe out there. In that case, the thread does exist and all threads exist. Okay, so maybe there's another thread out there that forms another universe, and none of the atoms from this universe are attached to the atoms of that universe. That's just academic, okay, just for food for thought. But the real issue here is what you see at the bottom. We either have the electron shells, they're spinning around, they swing the threads that come out of the shells themselves, or we have, like you see there on the right, bottom right, the rope disentangles and the threads come out. They could also come out, like I show there also in a second there, you'll see it, coming out of the row of electron shells. So it could be either way, okay? Either way, we can explain what magnetism is. What is magnetism? A bunch of threads that are swinging around. The magnetic field, that's what I'm referring to. Okay, another question. Fellow says, torsional waving is different because the strength of direction, counterclockwise and clockwise of a twist is the constant for the duration of the twist. There is constant amplitude along the rope. It goes around, instead of up and down. Okay, he's talking about the rope, whether it's going up and down or, it's going around. Okay, this is what he's referring to. Overlaying two twisting media of constant amplitude just results in double the amplitude no matter the phase shift, okay? Because he's trying to figure out how the rope causes interference, constructive and destructive interference, okay? In the case of the slit experiment, remember, or the needle experiment as I call it, that's a better experiment really. We have one rope hitting an atom in the on the screen, okay? And you have another rope coming from the other side of the needle or the other side of the slit going to the same atom. So you have two ropes going to that same atom, but they're offset by half a length. And so if they're offset by half a length, you get a destructive interference. And when they're both in phase, you get constructive interference. Okay? Where you have constructive interference, there's light. Where you have destructive interference, you have a dark band. That's essentially the theory. And it really, I haven't invented that. Not the part of thread, the part of rope, yes, but not the part of constructive and destructive interference caused by waves. That's been around for quite a long time. And it's that if the two waves, we're talking about, again, we're talking transverse waves, okay, meaning you have the electric field and the magnetic field, okay? So if the fields are in phase, constructive interference. If they're out of phase, okay, then destructive interference, okay? So that's the notion. That's where we get this, okay? Just so you can follow along. Okay, he says the only way to get destructive interference is to twist in the opposite direction with a rope countertwined to the first. Absolutely not, and you'll see this in a second. Or was I meant to understand that the structure of the rope wags clockwise and counterclockwise while twisting in both directions, one after another, imitating a transverse wave? No, you got it all wrong, completely right. Didn't get anything right. Okay, let's see what's right. Okay, well, from the rope model point of view. Okay, and the first thing we have to do is analyze this. Okay, so let's talk about this for a second. We don't see light itself, the electromagnetic rope. So it's not, you're not going to be looking at the rope. What are you going to be looking at? The atoms. That's, I hope that went through your head, okay? Not the rope, look at the atoms, okay? First thing. We can't see one atom. What we see is bunches of atoms. So when you look at the screen, like in a slit experiment, you're going to look at the fringes on the wall. Well, what are you staring at? Whether you know it or not, you're staring at gazillions of atoms in each one of those fringes. Okay, each one of those lines, you're looking at gazillions of atoms. It's not one atom you're looking at. Okay, but we're going to analyze one atom. What's happening to one atom? You're supposed to multiply it mentally in gazillions of atoms. What are we staring at? We're going to look at the rope? No, we're going to look at the atoms. Okay, you're focusing on the ropes. It's the atoms you got to focus on. Okay, let's get that straight. Constructive. Both ropes stimulate the atoms simultaneously. If they're in phase, let's see if I can do it with this. Let me move this aside for a second. Get this out of here. Okay. Let's see. We got blue. Where's blue? Blue here and blue here. See, the blue is to my left. Okay. Blue is to my left. So we're saying they're both in phase. But if one of these is turned around and you got red on the outside, blue on the inside, they're out of phase. Okay. But they both converge upon a single atom. They come from two different atoms on the needle or the slit. So one comes from here, the other one comes from here. Okay, so you got one here and the other one here. Okay, so they're going like this. They're meeting at that atom. If they're in phase, they're both going to stimulate that atom. Two ropes, one atom. Two ropes converging upon one atom. They stimulate it in the same direction because they're hitting it both with blue. Okay? And so they're both giving it the same impetus, the same pulse. And so the atom, what does the atom do? The atom was normal. It was, before you turn on the lights, it was just pumping its a regular speed. Now you turn on the light. You turn on the laser, right? That's going to hit him. Now it's going to stimulate that atom. It's going to pump a lot faster. So it comes within visible range. Blue with blue, they're in phase. They're going to give the same signal to that atom, the same thump. Okay? If they're offset and one tries, in other words, you get, again, red versus blue, right? One tries to give it a stimulus. The atom is trying to expand and contract because of that stimulus. But as soon as it tries to expand, the other one gives it a counter stimulus because it's coming half a link behind. So the atom's trying to expand when that second link comes in and gives it a second impulse. So it's staggered. The pulses are staggered. And the atom does not manage to expand and contract at the same speed as the one that's in constructive interference. Okay? Now that's the explanation. I hope you got some of that. You can always revise it later on. But here is the visualization of that. Okay, I've shown this in the past, but obviously this fellow did not see this. Okay, the one on the top, okay, you don't have the light turned on. Okay, so that's why I put the atoms in black, okay, showing that they're pumping at a regular rate, which is below the visible range. Okay, all you're seeing essentially is the screen. Now what happens? As soon as you turn the light on, you get the two beams or the two ropes, right, are in phase. because they are in phase, they stimulate that atom to go to a wider range. Okay, so it's pumping faster and it's pumping in, it's synchronized with the two ropes are synchronized. The one on the bottom, they're not synchronized. You can see that when one comes in and the atom tries to expand, the other one hits it again and doesn't allow it to expand. So it's the atom that's got the problem. The atom, because of the ropes, right? Because of the signal that it receives, or the stimulus it receives from the ropes, they're staggered. And so the second one is counterproductive to the first one. That's why you have a dark band. Okay? So I hope you look at that, and if you have questions, well, raise it again, but that's essentially it. You have staggered signals coming to a given atom. And again, we're looking at gazillions of atoms. So you've got gazillions of ropes, gazillions of atoms, and they're all doing the same thing. Why? Because when you have the needle or the slit, it really doesn't matter. I like it with a needle because you can get an atom on one side and an atom on the other side. They receive the same signal from the laser, but that same signal from those two atoms does not arrive at that single atom on the screen at the same time if they're offset by half a link. Okay, and because the rope has all these different nuances of torsion, right? Different degrees of twist. That's why you get a ring. See, when you look at the fringes, it doesn't go light and dark sharply. There's a gradient there that goes into dark and then a gradient where it goes back to light. And that gradient is because you have all these different turns of the rope. You know, you have different angles for each one of those ropes, the gazillions of ropes that are coming from the needle to the screen. So you got to try to visualize all that, that entire mechanism. Okay, final question here. Someone fellow says, ropes, a description of a belief. There's nothing of scientific method to back it, okay? Doesn't even come close to being a hypothesis, at least something in scientific method to back it up, I guess. Definitely not a theory level, meeting all of scientific method and constantly repeatable, okay? In other words, I think he's talking about repeating experiments, that you got to do some kind of experiment. Okay, what's the answer to all these issues that this gentleman raises? Well, science is not about descriptions or beliefs. So he got that first one wrong. Science does not do descriptions. Science does not do belief. That's religion. Math does descriptions. Religion does belief. Science does explanations. No evidence to back it up. Well, we don't use evidence in science. Evidence has to do with belief, which is religion. Okay, so look up where you see belief and you'll see that it's equal to religion. So evidence has to do with proving to someone, to convincing someone, persuading that person and converting him to your religion. You're recruiting him, okay? So no, we don't use evidence in science at all. Okay? Evidence is only used to persuade the jurors. Hypothesis, that's equal to an assumption. Okay, so a fellow said it doesn't come close to being a hypothesis. Yeah, it's an assumption. Rope is an assumption. We're saying let us assume that light is mediated by a rope-like entity. So it's an assumption. It's a valid assumption. Theory, what is a theory? It says definitely not a theory level. Yeah, a theory is an explanation. So we're explaining how light works. We're explaining torsion. We're saying that light consists of frequency and wavelength. What are we talking about? We're talking about lengths of links, and frequency is the number of links. So we can explain many things with the rope model. And yeah, physics explains mechanisms. So that's what physics is about. So we're within the laws of physics or the rules of physics or the foundations of physics, because what we do in physics is explain mechanisms, causes. That's what people want to know. People want to know how gravity works. People want to know what magnetism is, how Mother Nature does that magic trick of picking up iron filings with a piece of metal from far away. How does Mother Nature do that? That's what people want to know. And for that, you need physical objects if you're going to explain a mechanism. Okay? a cause. You can't do it with concepts. You can't do it with field. You can't do it with a wave. You can't do it with mass or any of those concepts, time and energy and whatever nonsense they've invented out there in mathematics. No, you gotta use objects. We want to see we want to see you make the film, the movie of how you produce attraction. And if you're going to do attraction, action at a distance attraction, hopefully you're going to do it with some mediator, physical mediator. If not, you're doing black magic. Okay, with that, I'll see you next time. We'll see you on Wednesday. And we haven't finished with quantum mechanics. We have some more properties, a couple of them left over still. So we'll see you then. Bye-bye.